Hi, this is a walkthrough video for the fluid pressure simulation activity. Before you watch this video, make sure you have finished this self-guided worksheet from experiment 1 to 2, 3, 4, 5, and also the investigation challenge 1 and investigation challenge 2. The whole virtual experiment will be closely related to the equation of liquid and gas pressure, which is pressure difference equal to rho GH, density times gravity times height difference. So if you haven't finished all the questions, you should pause the video now and finish it yourself first.
2,000 years later.
Alright, the first experiment is to go to simulation, enable the grid, and pull out the pressure gauge and put it at 2 meters. So let's do it. Grid, pressure gauge, and at 2 meters. So I think when you try to do it, you should look at the very pointy tip at the bottom and make sure that is pointing at 2 meters. Your reading may be slightly different from mine because it's quite sensitive, as you can see, right? So it might be slightly off from my reading to your reading, but that's fine. The next step that I want you to do is to open the water valve at the top and look at the pressure change, and also open the water valve at the bottom and observe the change. So what you should find is when you open this tab, you can see obviously the pressure go higher, okay, until you can't add any more because of the simulation itself. When you open the valve at the bottom, because the water are leaving, and so you can see the pressure go down. Interestingly, one thing you should also look at is when the water is no longer touching the pressure gauge, you can see it doesn't actually get changed. Alright, so it's only effective, of course, when you have more water or less water above the pressure gauge. Now, when you open the valve at the bottom, you are actually removing the water, and doing so would decrease the pressure continuously or regularly. And the reason behind, similar to what we just mentioned earlier, but the opposite direction, as in because there are less water above you now. So you're kind of feeling relief, alright, having less pressure. And that's because you're having less weight that is pushing down to you, and therefore you have less pressure. Except when the water level is below 2 meters, then according to the simulation, you could see there's no change, no effect in the pressure. Again, the yellow one are all observation. And the reason for this is because since when you keep removing water below the 2 meters, then that actually have no effect. It doesn't affect anything above you, right? And therefore there's no effect of the pressure. Experiment 2. It asks you to change the fluid density, increase or decrease, and see what happens. So let's try to do it. Of course, you have to make sure that there are some liquid above you, alright? Otherwise, if you have literally no liquid or liquid is below you, then of course it doesn't really change anything. Okay, so you really have to ensure that there are at least a bit of liquid above you. Alright, so when we decrease the density, you can see that pressure decrease, or when we increase, the pressure also increase. Okay, so this is simply the observation. Okay, so these are the observation, but then for the reason, there are actually two equations required. Let me give you 10 seconds to think about which two equations. Okay, the equations are, of course, related to density. Rho equals to m over v. Okay, and so if you have increased density, the mass is going to increase. Volume remain constant here, so I put a cross here because you didn't add more water or liquid in general or remove it. So the only thing that changed when you change the density is to change the mass here. If density increase, mass increase. However, that doesn't still link to the force eventually, because we should talk about force, not the mass when we talk about pressure. And therefore you have to use one more equation, that is weight equals to mg. And so here, g doesn't change because it's the same planet, but then if you increase the mass, then you increase the weight. And finally, increasing the weight would increase the pressure, similar to the experiment 1. And of course, for decreasing the density, then the whole thing will be opposite. I'm not going to write it down. You should be able to understand. Experiment 3. Now, similar to density, change the gravity. More precisely, gravitational field strength. Of course, in reality, you can't change it. You can't suddenly change a planet's gravity. So it can only be done in simulation. However, you can still be able to see the pressure change. So let's try to do it now. So I guess I'll change it back to water. And now what you can do is lower the gravity. Okay, so you can see, wow, it changed so much here. Okay, for the pressure, it become much lower on mass. And well, because that's the gravity becomes so small. And if you go to Jupiter, which is of really high gravity, you can see the pressure go much higher also. Okay, so quite similar to density. When gravity goes small, the pressure goes small. When gravity go big, pressure go big also. Okay, so here is the wording for the observation. And this time, the relevant equation is simply one of them. Alright, it's simply weight equals to mg, because this time, more directly, you are changing the g. So for example, if g increase, while m remain unchanged because you did not change density nor adding more volume, right? So mass is remaining constant. And therefore the weight should increase when you increase the g. Again, in practical world, it's not really possible, right? Only possible in this virtual lab. But then in this case, you will be increasing the weight and therefore increasing the pressure, vice versa. Experiment 4 is quite interesting. Let's have a look. So what you have to do is to change the scenario into the second one, which gives you this real shape. And what you have to do is go to the 2 meter, that one, and set up 2 pressure gauge. Or you can try to move the pressure gauge horizontally along the 2 meter and see whether or not there are any change. So if it is increasing or decreasing or what. So let's try it out. Okay, change it to second one, and yeah, I think that's pretty much it. We can reset the gravity or density. As long as it's fixed, it's fine actually. So what we can do is having one here. Okay, I try my best to point it to 2 meter, and I can have another one. I try my best, and also I'm not looking at the other one. I really try to align it to 2 meter. Okay, I think that's the one.
NANI?
Okay, so now when I look at these two readings, it's not exactly the same, unfortunately. In theory, they should be the same. Alright, so the reason why they are not exactly the same is because maybe I'm too old. And this is so hard to align, like to get the two exactly on the same horizontal level. However, if you simply try to move it horizontally, I'll try, okay? You can see, well, of course, this is not in liquid, so it doesn't show you the pressure. But as long as you are on the same level, the pressure are kind of the same, all right, and it should be the same, all right, on the same horizontal line. So this is one of the physical properties that you may find for fluid pressure. Okay, so pressure is always the same along 2 meter level is the observation. The explanation, however, will be saying they have the same height difference from the water surface to 2 meter level. And that is to say, if you don't know what I'm saying, that's actually referring to this water surface and this water surface, right? So if you think about the depth that they have been gone through is a constant from the water surface to that particular 2 meter level, which we put the pressure gauge on. So in that case, the weight acting on this line is going to be the same, and therefore the pressure is going to be the same. Experiment 5. This one is even more interesting. You have to pull the pressure gauge out of the liquid. So you are not doing liquid pressure, you are doing gas pressure. So let's have a look here. You can either do this scenario, or if you like to do this, that's fine too. So now you can see I don't have any liquid above me, but if I go up along the air, can you see that? the pressure would still decrease. Just like when you have water, when you go down, the pressure increase. When you go up, the pressure decrease. That is the same when you move through the air. And that is, of course, because air will also exert weight on you, right? Because they also have mass, they are also attracted by gravity, and therefore the pressure will also be changing along the vertical line. But the only thing that you see, the other thing that you see is it doesn't increase or change as much, right? It only changes by a tiny bit when you move up and down in the air. It's like the last two decimal point here. It can be displayed. While in the liquid, you can see it change drastically, all right, compared to the air. So that's the difference you want to explain later on. So here is what I will write. First of all, the observation. Pressure gauge moves up, pressure will decrease. Pressure gauge moves down, then pressure increase. These are observation. For the explanation, when we're moving up, less air is above the gauge, and therefore there will be less weight exerting on it. So imagine just simply when you go higher up, like if you try to count all the air above you, many layers above you, those air, you have less layers basically, and therefore we have less weight, and with the less weight you have less pressure. Okay, so the same idea will apply in the opposite way when you move down the pressure gauge. Question 3 is asking you how is it different when you move inside the liquid. And so as we observe, the change in liquid is much greater than that in the air. Okay, and that is because something to do with the weight or the density, of course. The weight, of course, that's also due to the density. Density of the liquid is much greater, and therefore the weight of the liquid per unit volume. So therefore I put a bracket with the same volume, because if you say more volume of air, then that's not a fair comparison. We are comparing the same amount of volume. So weight of the liquid per unit volume is going to be greater than that of air, and that's also related to density also. Air, you can imagine, is just an extremely small density of fluid in general. Finally, investigation challenge 1. So the task is to ask you change to the 4th scenario, which is this one, and in this case they don't tell you the density of the fluid, and therefore that's basically what I want you to find. Think about a method where you can estimate the density of it and show me how you can calculate that. And so obviously the only equation that we have learned and that's relevant to our task here is the one that is P pressure equals to rho G H. I hope now you finally realize why this is closely linked, because whenever you increase the density or increasing the G or increasing the H, then the pressure will increase. Okay, more precisely, when you write the equation, I would say write delta P, because it's a change of pressure, and here is a change of height also. So using this equation will be able to help you. So by looking at this equation, obviously, since we don't know about rho, which is the density, we need to know the other 3 things in order to do the calculation, obviously. For G is given, you can see from the simulation itself. Let's just take it as the Earth, and then for delta H and delta P, this is something that we want to find, and let's try it. Okay, so what I'll do is, for simplicity, I'll just fill up the whole thing with liquid, and so 1 meter will really be having 1 meter of liquid above you, right? And so if I pull the pressure gauge, if you like to, you can use a ruler also, but I don't think it's necessary because I'm aligning with 1 meter anyway. So 1 meter is here, and then later I'll need to measure the 0 meter, which is this one, so that I can find the delta P. So let's record the greater one first. So that hopefully is accurate. 117.6. 117.6. I'm not going to take the last 2 digits because, as you know, that kind of fluctuate depending on my hands, so that's not going to be reliable anyway. And then moving to the 0 meter, that should be 101.3. 101.3. Notice one thing, unit, very important. This is in K Pascal. That means your measurement is actually in 1,000, 10 to the power 3 when you substitute the pressure in it. So this is something you have to be careful always in physics. And then rho is the unknown, we don't know. G is 9.8 according to the simulation. H, if you really like to say, 1 minus 0. Alright, and it is in meter, so very good in SI unit. So eventually you should get an answer like 1663. Yeah, 0.2. I think 2 sig fig would be very good enough already. So 1.7. Okay, let's take 3 sig fig. So 166 then times 10 to the power 3. That's the density. So density should be kg per meter cube. That should be the unit that you're having, because the rest are all in SI unit. So density should be in SI unit also. Okay, now we have to go back and add the description of the method. So what I'll say is measure the pressure at 0 meter and 1 meter, okay, with the liquid full, like filling in, so then that is really 0 meter and 1 meter depth of the liquid. And then, yeah, knowing that G equals to 9.8 meter per second square, and then sub all the numbers, basically what we have, sub all the values into the equation. Okay, so I guess you can expand the description here. So question 4 is simply the same task, so asking you to switch it to fluid B simply. So at 0 meter is still the same pressure, because it actually have nothing to do with the fluid anyway. It's not something to do with the air itself, and you didn't change the air, so it's still 101.3. 101.3. Okay, and the one at 1 meter, or if you like, you can do 2 meter actually, but then you have to divide by 2 later on, so it's going to be the same. 109.2. Okay, 109.2 or 0.3 if you like to. Okay, bracket times 1,000, and then rho is unknown, G is the same, meter is height is in 1 meter. So again, use your calculator. The answer that you find, let me just label better, rho A and rho B. Rho B is going to be 800 something like that. Okay, round it up to 3 sig fig, so 8.16 times 10 to the power 2. Okay, same unit, kg per meter cube. So if you really are interested and curious like what kind of liquid it would be, then you can, I guess you can go and check out the list. Or here, not really. I think, yeah, 1.66 is even more dense than honey, right, for some reason. So 800, not sure. Yeah, 800 should be something like this, right? So not yet gasoline, but then it's lower than water somehow. So I don't know what that is. You can go and check the list on Google. Investigation challenge 2 is almost the same as 1, and therefore it shouldn't be that challenging to you now. The task changed to mystery planet. Okay, so the gravity is unknown, but then you can get to know the density. Okay, so what you can do is to change to here, mystery planet. For simplicity, once again, I'll get it full with water. Full density will be 1,000, and the approach is the same. Measuring the 0 meter and then 1 meter. Okay, and then we'll have to apply the equation. So let's put it down again. Delta P pressure equals to rho. So be careful, these two are different symbol. P is right this way. Rho is written this way. Rho G delta H. Okay, so again, I'll just play safe. Do 0 meter and 1 meter. Again, if you like to, you can do other things. You can actually do 1 meter and 2 meter, because when they minus, the delta H is still 1. Anyway, it will still work all the same. Or maybe I'll do it this time then. 246.7. Okay, for 2 meter, and then for 1 meter, it's going to be 226.5. Okay, again, it's in K Pascal. Rho is 1000. G is unknown. Delta H is 2 minus 1. And so actually the 1000 will cancel, and so I think G would simply be found directly by subtracting these two. So 20.2. That is a great deal, a lot, right? Because Earth is like 9.8 and this is 20.2. This is like a double of the Earth. Alright, so I'm just really curious what it would be, so I go and check out the surface gravity of different planets. So here's a list. G means the one that is referenced to the Earth, and therefore Earth is defined as 1G, being like the standard. And so we are trying to find out, because we got 20.2, so roughly 2G. Then along the whole list, okay, 0 point something. Okay, Jupiter is 2.5, not very close, but at least it's 2. This is 0.1 something. Saturn is very close to Earth. Yeah. So that is to say, the planet A doesn't really exist. Okay, going back to question 2 again. The method again is very similar. Measure the pressure at 2 points. So I'm not going to be very specific here. You can choose whatever point you like, as long as it really matches with your calculation. That's fine. Okay. With the known height. So here it will be 2 meter and 1 meter. Okay, which is known. Of course, you can measure it. And also knowing the density, and then you can substitute all these values into the equation, which of course will be this one, and leaving the only G being the unknown, and therefore you can calculate the value. Okay, so unfortunately, planet A is not really a real planet. Let's try planet C. Planet C, okay, let's try to do 0 meter and 3 meter this time. So we would have 86.5. Okay, so this time I think I'll just write down the equation, 86. the value directly, and then 67.2. Okay, it should actually be 0.6 times 10 to the power of 3, and then we have the density, and then we have the G to be unknown, so this time I put GC. Okay, it was GA, and then the height difference was 3 minus 0. Yeah, that's the one that we measure. So eventually we can calculate. That is something close to 6.46 recurrent. So I will run it to, yeah, I think 3 sig fig is pretty good. So actually I should write more than 6.47. Okay, you can either write Newton per kg, or you can put down meter per second squared. And so these should be roughly 0.6 G of the Earth, right? Because Earth is roughly 10, so this is about 0.6. Checking the list again. Okay, please tell me that this is a real planet. I think the closest one that I get is about 0.8 something or 0.9, which I don't feel it is really close enough. So planet C is also fake. Hiya. So that is all for the simulation activity. If you enjoyed this video, hit the like button now and subscribe to my channel. In the next video, we'll talk about how to derive the equation P equals to rho GH. I'll see you again in the next video. Bye.